two shaped siphons, U-shape and M-shape. And let's see what happened. So I'm gonna start with U-shape. So 3, 2, 1. So you can see that the water rises up and it's dropped down and cannot be a self-starting siphons. And how about M-shape? Let's try. So 3, 2, 1. Whoa, the water comes out and it can be self-starting siphons by its own. So let's see why. So now we're gonna prove that why U-shape cannot create a self-starting siphons. So I have a bucket of water and U-shaped siphons, and I set 2 points, which is A and B, to represent pressure inside the tube and the pressure outside the tube. So from P equal to F, this is force over area, and F here is mg. So we can have mg over A. And from the density equation, which is rho equal to m over v, so we can have rho vg over A. And v is equal to A times h. So we're going to have like this and cut A. So the final equation is P equal to rho gh. So we're going to look at the h. So A and B has the same height. So it can mean that the pressure A, which is inside the straw, and the pressure outside is equal. So let's move on to M-shaped self-starting siphons. So from hydrostatic pressure, this illustration illustrates that the air pressure will push the water and the water will try to come inside the tube, but it will stop here at the level that the pressure outside and inside is equal. So from this M shape, it will also have an air pressure that will push the water to come inside the tube, and as the tube, the first curve is under the water, so the water here can cross the curve, and from the cohesion force, which will be here, that will connect the water molecules, so it connects and go along in the siphons and go out here. So now we're gonna further explain about the M shape by Bernoulli equations. So point A, we have PA plus rho gh1 here, while point B only have PB, which is the air pressure. So point A will have more pressure than point B, makes the water flow from point A and comes out at point B. But when the level of water drops down to reach point A, rho gh1 will not have any more, makes two of this one, PA and PB will equal, and the water stops. Now we're going to do an experiment about different length of first segment, with a length of 2.5 centimeters, 4.5 centimeters, and 5.5 centimeters. So now I have 3 siphons, the shortest, the medium one, and the longest. Then we record the result. From the result, you can see that the average flow rate of A3, which is the longest siphons, was the lowest, while the shortest siphons have a highest flow rate. So from this equation, I divide into 2 parts, the straight part and the curved part. You can see that both of them has friction. So from this equation, work of friction is equal to friction times distance. So distance is the distance that water takes to flow along through the tube. So the more distance, the more friction. But the more friction, the lower acceleration. So the lower acceleration will affect the lower velocity. The lower velocity affects the lower flow rate. So to sum up, the longest tube has the lowest flow rate. Our study shows why an M-shaped siphon can self-start while a U-shape cannot. In the U-shape, both ends sits at the same height, so there's no pressure differences to expel air and begin flow. But the M-shape creates an initial pressure gradient that pushes air out and forms a continuous water column. We also found that increasing the first segment length reduces flow rate because of greater height, friction, and bending losses, resulting in higher total energy loss. Thank you.